Okay, so how's everybody doing? How many of you have, well, how was this most recent assignment? Difficult? Easy? Si- 6 or 7 what? The most recent one, the one that you just handed in, yes. Yeah. It was okay? How was the level of difficulty? Yeah.
Dealing with the pygame.rotate, that was weird.
So dealing with pygame.rotate was weird because
The bounding box only increases in the positive direction, so it shifts over the image.
yeah. So that's one thing is when you rotate a square that's aligned, whose sides are aligned with the axes, then you have to fit that into another square whose sides are aligned with the axes, or a rectangle or whatever. That you get a bigger rectangle or bigger square. And so for some of you that may mean that the ball that was supposed to be rolling along the bottom was actually somehow rolling along the corners of a square, plopping up and down. Yeah, so you have to be careful about that, and just it helps if you have a routine which draws it at a centered version of it, and you make sure the center doesn't go up and down. You just keep it a fixed distance away from the walls. Any other comments about that assignment? Yeah.
I found the instructions were unclear for one of the questions. It said it was like clockwise around the screen.
Yeah.
And I thought it meant like clockwise like that way, but it would mean clockwise rotating. So I got Dr. Mark.
Does it say clockwise or counterclockwise? It said counterclockwise around the screen. Yeah. Anyway, yeah, okay.
Was it rotating or was it around the screen?
So the ball moves counterclockwise around the screen. That means that the ball itself will be rotating clockwise.
Okay.
Will be rolling clockwise. Any other issues? Yeah, of course. Yes, in the back with the glasses.
Would I be able to talk to you after about my assignment so I have some ideas to how that compares?
Yes, yes. I haven't marked it yet. That's why I haven't been able to get back to you. Any other feedback? Anybody been to a tutorial yet this week? And how did that go?
Well, we got the first question.
Okay, good.
I'm finding more thinking most of the steps. Like I'm thinking of how do I do this, but it's just like a simple couple lines of code.
Yeah, that's why it is good to think about it first, because if you spend enough time thinking about it, you will come to the realization that it is just a few lines of code. If you just start coding right away, you'll end up with dozens of lines of code that could be done in 2 lines of code. Okay, and now an opinion poll, I guess. So no matter what happens, this next week's assignment is going to be making a game in Pygame. So you remember assignment 3 was you learned a little bit about how to do things, input and output and so on, and then you made a game of your own choosing. It had to have meet some requirements. So next week it's going to be the same thing with Pygame. So start thinking about that. But what I'm more interested in now is the lecture material. So what I should be lecturing about. So next week I can continue to do another whole different game in Pygame, or we can move on to the next topic in the course. So I would like some feedback on which of those things you would prefer. The next topic is algorithms. Okay, we're sick of Pygame now. Good. So anything that you need for your game, you can then figure out for yourselves. Good. So next week for you guys means starting Friday. Yeah.
Just about Pygame, anyone running a Retina display MacBook?
Pygame renders at quarter resolution. So
Pygame renders at
the
quarter
window is the right
resolution.
size, but whatever is inside the window is only in the top left corner. It's 1/4 the size because every pixel normally is 4 pixels on a render display.
And Pygame just does 1 for 1.
I mean, it doesn't support.
Yeah.
It uses pixels as a point, so it's,
Yeah. Okay.
it doesn't support rendering. It's kind of
Okay.
unloving.
So.
So especially with the physics that we're doing on set 7 where it follows the mouse, that can really get screwed up because the mouse, where Pygame thinks the mouse is not exactly where the mouse actually is.
Yeah. Yeah, I don't know. So Pygame doesn't support every platform perfectly, and this 4 for 1 Retina display thing is kind of a weird hack anyway. But yeah, I don't know what to tell you. Find a crappier computer to work with, I guess. Yeah, it doesn't. It's basically there has to be a compromise because too many applications are hard-coded into thinking that pixels are reasonably large units of screen real estate, and with the really good displays, that's not true anymore. So they had to do something to make those applications keep working, and that causes some issues. Okay. All right. So then, so this will be our last class where we talk about Pygame, and so that's good. Then we move on to some algorithms and algorithm analysis. Next week, you guys will be doing an assignment still in Pygame, so you can ask me questions. If maybe I can answer them, maybe I can't, and we'll do that. What else? Anybody been working on this assignment? I know you have. Yeah. How's that going? Is it clear what's being asked? Because unlike the previous assignment where the videos were a pretty good explanation of what things should look like, it's not obvious really from watching the video of this ball chasing the mouse cursor around exactly how that's happening, but there's some instructions on how that should work. Yeah.
I find with my code, it's like it does the same thing as it does in your video, but it's a lot more laggy for some reason.
It could be the speed of your machine, or it could be that you're doing something really inefficient in your code.
Okay. I use the direction equals 0.9 times direction plus speed.
Yeah, that's not a big calculation. That shouldn't be an issue. If the image is too big, it could be an issue. Transparent, transparency is a little bit expensive, so I just use it because it's the easiest thing. Some game developers would tell you to use a different transparency model to make it faster, but I doubt it's that. Maybe the size of your image. Try scaling that down. And it's actually really hard to play, right? You notice in the video,
Yeah.
I die twice, like instantly. So I don't know. Slow it down. For the third question, you can slow it down initially and have it speed up, or however you want to do it. Okay. So last class was for you guys October 25th, and I think we did this thing. So this was a game with an ant runs around, eats food, and eventually dies when it runs over poison, and your job as the player is to click the poison and get rid of it. And it wasn't a super polished game, right? I think we have a limited number of lives. Let's see. Yeah. So at the end of the game, there's a game over after 3 lives. But if you look at, there's somehow a lot of polish. So I can click again to play, but nothing told me that when there's something wrong with the life counting. And somehow when the game fires up as well, it's a little bit panicky. The thing just takes off. And there's no increasing difficulty, no score that we can see or anything like that. So I spent an hour or so this morning polishing this. To add some of the missing features. So first thing you'll notice is there's a number of lives up here on the left, score on the right, and it doesn't just fire off into the game. There's time for the user to figure out what's going on. There's a click to play message, which presumably means you click to play. Last minute change broke it. So now there's a different soundtrack. There's also sound effects. So I don't know if you can hear them. The ant eats something that sounds like chips when it reaches these things. And when it gets poisoned, it gets poisoned, so it makes a poisoned sound. As well, if you play this for a little while, every time the score increases by a multiple of 1,000, the ant speeds up. And every time the score increases by a multiple of 5,000, more poison starts appearing. You could do that. And then there's a scream with the game over. And then it goes back to this click to play business. So a few little touch-ups that make it considerably more like a game. And you maybe didn't see it, but unlike the previous game, when you die, there's a death scene and then it starts again. So there's a pause there rather than just you die and instantly you're back in the middle of the screen. And the same thing happens again when you die at the end of the game. Okay, third death scene, game over, and then back to click to play. So this is a fairly common kind of thing that happens in a game, is there's many different states that the game is in. Playing the game is one of them, and then there's all these things in between. So think about bigger studio games that you play. You maybe get to the end of a level, there's a cutscene, so that's a whole different kind of state that the game is in. Then the game starts out. Sometimes you may die, and then there's a whole death scene that unrolls. So there's all these states, and very quickly these things can get complicated. And so today what I want to talk a little bit about is a tool that actually comes from theory, but that's really useful for keeping track of these things. It's called finite state machines, or finite automata. And so if we try and use a finite automata to model our game, then we end up with some model that looks like this. Right now, our game is somehow in our waiting to play mode. Okay, so this is a state, and our thing, this happens to be called the starting state. And in the starting state, not much happens. The ant doesn't move. There isn't even any music playing or any of that stuff. The next state we that occurs after that is the playing state. So in that state, the ant is moving. We're checking for poison. We're doing all kinds of things. We're checking if the ant's eaten anything. There's a lot of stuff that goes on that state. We're looking for mouse clicks on poison, lots of things there. Eventually the ant swallows some poison, and then it goes into the dying state. So this is a pretty good metaphor for life. You know, initially you're in your mother's womb, and you're just waiting to come out, and then you find the right button to click, and out you pop. So you click a button and pop out, and then you're playing for a while. So that's what you guys are doing now. Most of you don't have full-time jobs. You're just in school playing around, having a great time. Well, I hate to break it to you, but pretty soon you'll reach my state, which is when you start dying. And well, I'm afraid it's not too long before it's game over. So if you eat the poison enough, you get poisoned enough times, you don't just die, it's the end of the game. So that's how life ends. Too much poison, exactly. And believe me, I poisoned myself plenty when I was playing the game like you guys. So. Yep. And so these things are called states, and in the theory world, they're also called states. These things are sometimes called finite state machines or finite state automata. And you have these states, and you usually draw some arrows between them. So from the starting state, there's an arrow to the playing state, and you usually label the arrow with what has to happen for that transition to occur. So to go from starting, which is showing this screen that says click to start, to playing, the event that has to happen is a click. When you're playing, in order to start dying, you have to eat some poison. So that's the arrow there. And when you're dying, once that's over, there's some sort of event, which is that the number of lives is equal to 0, takes you into the game over state. But there's a couple of other arrows here. Yeah.
The question about the point of game states.
The point of them?
Yeah.
In what sense?
Well, like, I didn't really understand how you implemented them very well last time.
Okay, we'll go over the code shortly, but right now you should just think of these things as what the game should be doing. So, right, it's certainly different. There's the mode of operation right now, even though it's still refreshing 30 times per second, this is certainly a different thing that's going on now, or a different state to be in than this, right? So we should, the states capture this. So for example, here, when I click, I get rid of poison. Before, when I clicked, I would start the game. And even this dying is something different, because now clicking doesn't do anything while you're dying. The ant stops moving. There's a bunch of things that are different about dying, and then ultimately game over is even more different. There's a message that pops up that says it's game over. So that's why we have different states, to keep track of how the game should be behaving. And now we want to look at the transitions between these things. So there's a couple of more transitions. One of them is from the dying state. We sometimes go right back to the playing state. So if the number of lives is bigger than 0, it's not game over. We just decrease the number of lives and go back to playing the game once we're done dying. And it's not clear, at least until we look at the code, what made that happen. So it's clear that clicking is what made the starting happen. It's clear that eating poison is what made the dying happen. But why did we start playing again? What caused that to happen? And similarly, from game over, there's a transition all the way back to the starting state, in which we say, you know, okay, we've played the final death scene, and now we let the user play a new game. And so why does that, and when does that happen? So we should look at the code to see what's happening here. So let's take a look at this thing. We won't go through all the code. We'll just look at the highlights. So in the init method, that's when we go to this starting state. So we set the state of the game to game.starting. And if we look at the different places that game.starting shows up in the code, well, we see that at some point when we're handling events, if there's a mouse button down and the state is game.starting, then we call a function called self.restart. So that's why when we click at that point, the game restarts. So we start a whole new game. If we search some more for that, there's another place where we see that state showing up, the starting state, and that's in the draw method, which draws the entire contents of the screen. So after it draws the ant, it draws the food, it draws the poison. If the state and the score and the number of lives, if the state is game.starting, it draws this extra thing, which is this message that says click to play. So in the starting state, there's a bunch of different things that happen. So clicks means something special for starting states. It means restart the game. Drawing is a little bit different. We put this message up that says you can click to start the game, and so there you see. From there, from this starting state, we saw that if you click, this restart function gets called. And well, when we restart, we set the number of lives to 3, we set the score to 0, we reset the ant's speed. That's because the ant has been getting faster and faster when the player was playing the game. Now we want to reset that to the original speed, the starting speed. And then we call self.start, which does a bunch of other things, including starting the soundtrack, resetting the ant's position to the center of the screen, creating a bunch of new food, a bunch of poison. The ant chooses the food, and then we transition finally into the playing state. So that's this transition here. A click does all of that, sets everything up, and takes us into this playing state. And as we play for a while, one of the things we check is if the ant has been poisoned. If it is, we call this function called self.die. And if we look at what die does, the music stops, number of lives goes down by 1, we enter the dying state, we play the sound of the ant dying, which is that horrible choking sound, and now we actually set a timer. That timer is supposed to generate an event that's called start, and the delay on that timer is the length of the dying sound plus 1 second. And so actually, if we look at this picture, we now know what causes this to happen, it's a start event. Eventually the timer that we set there fires off after the sound is done playing, and we've waited a respectable amount of time to mourn the loss of that ant. We will receive a message, an event, which is this game.start event, and then one of two things can happen. If the number of lives is 0, we call game over, and if the number of lives is bigger than 0, we start. So both of these transitions are triggered by a start event, and which one we actually take, whether it's into game over or playing, back to playing, depends on the number of lives. Okay. And if we make it into the game over state, so if we call game over, we set the state to game over, we play the game over sound, and again we set a timer. This one sends us a restart event, and again the length of the timer is long enough to play the sound plus 1 second. And so this last transition from game over back to waiting for the user to start is actually triggered by a restart event. So this is a fairly simple game, but it still has 4 states, and there's some interactions between states that you really need to work out carefully to make sure the game does what it's supposed to do, right? And careful managing of these states. And what's more troublesome, and the reason I think that these diagrams are useful, is that the actual implementation of this finite state machine with these 4 states is spread out all through the code, right? I mean, there's places where you die, and somewhere else where you restart, somewhere else where a click happens that puts you into some state. It's just spread throughout the code. So, as somebody who comes to this code and has never read it before, it can be difficult to understand what's going on. And even as somebody who wrote the code, it can be difficult to make sure that all the things are happening that should be happening. So when designing these things, it's actually helpful to make one of these diagrams and think about the way a game should play itself out, and draw this machine and then implement that machine in the code. In fact, there are whole software development methods in which the way people program is by drawing these little machines and maybe inserting a little bit of code inside of each of these states and then pressing a button that says, okay, give me the code now. So the whole UML modeling language is based around this idea that programming you hardly ever have to do. You just draw some little figures like this, and the programming is something the computer does for you based on the figure. Some people believe that. But these finite state machines, whether you use them to help you figure out your game or not, it's good for you to know they exist. You'll see them again in theory courses. You'll see them again in software engineering courses. So now you've seen them here. This is just a good, very brief introduction to them. Okay, so any questions about that? It's just a tool to help you sort things out in your own mind. And these are fairly common. These kinds of state machines show up fairly frequently in things like video games, in things like user interfaces, in things like any kind of web application, right? Think of what's happening in a web application. You're essentially constantly changing states. You go into your email, you're looking at a list of conversations, that's the conversation view state. You click on one of them, now you're looking at an individual email, that's a different state. You go change the settings, that's a whole other state. So there's there's many of these state machines show up all over the place. Okay. So there's still some things that I'm very unhappy with in this game. And one of them is just the way the ant moves. The ant is pointing northeast, and it doesn't matter which direction it's moving in, it continues to point northeast the entire time. So even if it wants to go southwest, it'll just back up in that direction. I think it would be a little bit nicer if the ant would at least face in the direction that it's traveling. So let's see if we can make that work. So we have this ant, and we have a bunch of objects in our game. Ants, poison, food, and game object, which is this thing that's above all of them. So everything is a game object, and if you recall, game objects can do a few things. You initialize them, they can draw themselves onto a surface, and they can return their size. Now, ants can do a little bit more than that. Not only can they do all those things, but they're also able to choose food from a list of food, or some collection of food, and they're able to move. Once they've chosen food, they're able to move towards it. And this is this move that does this trick of computing a unit length vector that points from the ant towards the food, and the ant takes basically a step along this direction. The length of that step is controlled by the ant's speed. Now, we want to make a change to this game, which is actually entirely, at least for now, is just entirely for the looks of things. It doesn't affect at all how the game works. It won't affect gameplay at all, but it will just be basically the way the ant is displayed to us will change. So it should be pointing in the direction that it's going to. And so this involves a change to the game, and then the question we should ask ourselves is, well, what is it that we need to change? Yep. So we need to change the rotation of the image. And when is it that we should do that? Or how should we do that? Yeah.
Every time it moves from one piece of food to moving towards another piece of food.
Okay. So every time the ant's direction changes, we should change the image in some sense. Change the image that we draw. Now, did any of you run into any problems with your image eventually blurring out? Okay, so if you repeatedly rotate an image, so you take an image and you rotate it and you rotate it again and again and again, eventually you'll just get this big sludge of junk. And so when you're doing that kind of stuff, really what you want is one image that's the true image, and then what you do is repeatedly rotate that true image. Not rotate an image and then rotate the resulting image and then rotate the resulting image. For one thing, the thing will just keep getting bigger and bigger if you do that, like a snowball. So we still want to keep track of this one true image, but maybe we want some other version of that image. So let's try the easiest thing first. So when our ant, well, let's do something really easy first that won't affect anything. So you've pointed out that actually when our ant chooses its food, we already know which direction it's traveling in. And so this whole computation here that we do in move, which happens 30 times per second, actually we don't need to do it every time. We only need to do it when the ant changes the direction that it's traveling in, and the only time that that happens is when the ant chooses new food. So let's chop that code out of there and move it up into this section where new food is chosen. So you pick this new food, that means you pick a new target, you compute a unit vector that points towards that target, and then we can save that thing. So now we've saved the direction of this thing, and now every time we move, we just have to move in that direction that we've saved. So if nothing else, this should be more efficient. So let's just make sure we didn't break anything. Still seems to work perfectly. If anything, it'll be more efficient because there's whatever 6 or 7 lines of or 5 lines of code that we took out. It's not happening 30 times per second now. It's only happening once every time the ant chooses a new target. Okay. Now we would like to change the picture of the ant, the way the ant appears when it's moving in a particular direction. So there's a few ways we can do that. I think for the way that we're going to proceed, we'll do maybe what's not the most efficient thing, but it'll be the most practical for where we want to get to eventually. And that's just by redefining the ant's draw-on method. So remember, game objects have this method that allows them to draw themselves onto a screen. Ants are somehow different, and we would like them to draw themselves differently on the screen than other game objects. So we'll just override that method so that ants do it themselves. And now we want to draw this thing pointing in the right direction. So how do we do that? So we have this image of an ant. We can take a quick look at it. That's what our ant image looks like. It's pointing up there. That's the one we've seen every time. So how do we draw it the right way? So we know the ant is traveling in this direction, self.uv, and we'd like the ant to be pointing in the same direction as that. Yeah?
Well, naturally it's pointed at like 45 degrees, right? So we have to first kind of orient it so that we know where kind of its natural position should be.
Okay. So that means at some point we will do something like add or subtract 45 degrees to something. So what's the function, let's say in Pygame, that's going to do that for us? Yeah? Yeah, so Pygame has this rotate function, and so eventually we're going to use this, and at the end, to make it work out perfectly, we'll have to add or subtract 45 degrees. We'll figure that out shortly. But before we do that, what do we need to do? So we can make a picture of what we have here. Well, so rotations take some kind of angle as an argument, right? And what do we have? We have a unit vector, yeah? Well, they take a rectangle, so the thing that we'll be rotating will be self.image, and then, I don't know, some angle that I don't know yet, plus or minus 45 degrees. So we need to get an angle out of this. And what do we have? Well, we have a unit vector, this vector uv. So if we look at what we have, y-axis and x-axis, 1, 1. I can draw a circle here. And the ant wants to go off in some direction. And that direction is given by uv at 0, uv at 1. We'll call those things x and y. So a unit vector really is that, right? You can think of it as an arrow that starts on the origin, and it points to a spot on the unit circle, the circle whose radius is 1 centered at the origin. So we have this unit vector. The ant wants to go off in that direction. Now we need to turn this thing, which is just a pair of coordinates, x and y, we need to turn it into an angle. So what we would like to know is something like, well, this angle here. It's a good starting point. The angle that we make from the x-axis. So anybody remember any trigonometry? What's that? If you use opposite over adjacent, what is that? So tan is equal to, well, I'll call that y over x. Cos is the one that's equal to x, and sine is the one that's equal to y. But all of those things, those are functions that take an angle as an argument, and they give you back an x-coordinate, a y-coordinate, or the ratio between the y and x coordinates. But what we have is a pair of coordinates, a point, and we want the angle instead. Yeah.
You're not quite just getting the x or the y from your sine and your cosine. It's still a ratio. It's a ratio of the x versus the hypotenuse or the y versus the hypotenuse.
Well, the sine and the cosine give you the x-coordinate and the y-coordinate respectively, and then the versus the hypotenuse agreed. In this case, we have a unit vector, so there's no multiplying. I mean, the length of the hypotenuse is always going to be 1. But do these functions, are they even the right things for what we need to do? Yeah.
Since we have the ratio of x and y, we can do inverse tan.
Yeah. So what we want is something different, which is somehow the inverse tangent. We know y and x already. What we want is, what's the angle that gives us that y and x? So we'd like something like the inverse tangent of y over x. Now, unfortunately, the inverse tangent isn't good enough because it's unable to distinguish between things that are in the, let's say, the upper right quadrant and the bottom left quadrant. Because in one case, both the signs of y and x are positive. In the other case, they're both negative, but the two negatives cancel out, so you end up with a positive result. And so if you look in almost any language that has a math library, there's usually an inverse tan function. It's called a tan. So all these things are called arc, cos, arc, sine, arc, tan. They're the inverse functions. But you usually find an a tan 2, which doesn't just take the ratio of y divided by x as an argument, but it actually takes two arguments, the y and the x argument separately. And given those things, it actually has enough information to give you back the actual angle. Okay. So it's really important to read the documentation carefully here. This says returns a tan y over x in radians. The result is between minus pi and pi. And it's the vector in the plane from the origin to xy makes with the positive x-axis. So that's what we want. And the point of a tan 2, the reason it exists instead of just a tan, is since you know the sign of both inputs, it can handle vectors in any quadrant. Okay. So this thing here, this angle that we're interested in, is actually a tan 2 of y comma x. Okay. All right. So let's put that in there. So we want some angle, we'll call it theta, is equal to math.atan2 of the unit vectors y coordinate and the unit vectors x coordinate. All right, we're golden. All right, so we have this angle theta. So now what do? We just plug this into the transform rotate? Yeah.
You convert it to degrees.
Aha, good catch. So going back and looking at the documentation we have atan2, first line says it returns this thing in radians. So remember, radians are these basically numbers usually between 0 and 2 pi. atan2 does it a little bit differently. It gives you minus pi and pi, things between minus pi and pi. And then if we go look at the transform rotate documentation, they want a angle represented in degrees. And degrees aren't between 0 and 2 pi, they're between 0 and 360. And so we need to do a conversion between radians and degrees. And so let's look at how we can do that. There it is. In the math library, there's a function called degrees that takes an angle x expressed in radians and converts it into an angle in degrees. We could have easily rolled our own, but why not use something that's already there and tested? Okay. So just so we don't make a mistake, we'll call this thing theta r for theta expressed in radians, and theta d for theta expressed in degrees. Yep.
Could you just call the math one line?
Yep. Could have.
Also, it's theta r.
Theta r. Yeah. Good one. Okay. So now we just plug this thing in there, right? So I don't know. We don't know whether it's plus or minus 45 degrees yet. So is this going to work? Yeah, okay. So set the image and then say draw centered. We want to draw the image on the screen at the current position. So is that going to work? Let's see. We thought very hard about it, so it should be fine, right? Let's try. Crash. Global name UV is not defined, and that's on line 82. 82. And there's actually going to be another issue that I'll fix now before it pops up, which is not quite, eh? It is rotating, and it's rotating by a reasonable amount, but somehow not doing the right thing. That looks right, yeah. That looks worse than ever. That means, that shows that we tried and we couldn't do it. Yeah.
Is there any big performance boost of using a tuple over an array, just storing the vector?
No,
Or, I mean, what's
not really, no. Yeah.
Is it better for the edge to stop moving then turn, or turn slowly moving?
Well, let's get it pointing in the right direction first. So, anybody know what's going on here? What's wrong? Yep.
I think I can guess, but I haven't actually seen it.
Yep.
But I'm feeling that since you're just rotating the image, if it's naturally drawn to face right, the moment you want to move left, it's going to be upside down.
Not exactly, but it is a problem similar to that. Yep.
The problem I had
Yeah.
Sometimes it would return a negative value, which would then, when I tried to rotate the image, it would say, okay, you're going to rotate it in the exact opposite direction now.
Okay, so that's a good thing. Is somehow there's something, a sign problem maybe that's going on here. Yeah.
I was thinking maybe the rotation actually meant what?
No, so math or pygame.transform.rotate definitely uses degrees. So we're good there. Yeah.
Are you just rotating the same image? Like, so to point to the food, you rotate the image.
Yeah.
Or you just continually rotating the same image?
No, we're basically every time we draw it, we're creating a new image that's rotated to point to the food. Not the most efficient, but it's easier for tracking down bugs and easier for what we want to do later. Yep.
Did we account for the initial 45 degrees?
No, we didn't. So let's try and account for that and see if that helps. But I can tell you that it won't.
It would just be whatever you have minus 45 degrees.
Yeah, so let's see that. So the ant is pointing northeast, so 45 degrees up and to the right. And so the origin in all of these calculations that we're doing is pointing directly to the right. So let's see. Pygame rotate says what you specify is an unfiltered counterclockwise rotation. So if I give it a positive angle, it'll rotate counterclockwise. And I actually want to rotate it clockwise by 45 degrees, so I should give it a negative angle. So that would be using theta d minus 45. But our problems were a little bit deeper than that. So one thing that's interesting is something did work for us. Notice now at this initial state the ant is pointing directly to the right. And when we initialize the ant, we set its vector uv to be 1, 0, which is actually pointing directly to the right. So that's correct. And actually, even deeper than that, this is correct for some reason, but everywhere else it starts to go crazy. But now it's correct. So what's the angle? What's the angle when you're pointing directly to the right? Yeah? Go ahead. Yeah. No, that will maybe do it, but it doesn't really explain the problem as nicely as what's happening, as this picture does. So this picture, does it look like the normal picture that you're used to when you do trigonometry? What's weird about it?
The axes are kind of reversed with the y.
Yeah. In a normal trig picture, when you measure an angle, this would be the angle that you're talking about. Right? They start here at 0, and then the angles increase all the way up to almost to 2 pi as you go around. But here, I somehow measured out this angle for some reason. Well, and the reason I did that is because in a normal trig picture, the y-axis points up. And in fact, in every other discipline, except computer graphics, the y-axis points up. In computer graphics, it points down. That means, well, when we measure angles like this, we're actually measuring them clockwise instead of counterclockwise. And if you recall, the transform documentation says it wants a counterclockwise angle. So actually, all we have to do is negate the angle. And so where did we go? Instead of using theta d, we can just use minus theta d. Because And that's why when the angle is 0, this thing actually works perfectly, because 0 is equal to minus 0. So when it's pointing directly to the right, it works great. But then when the ant should be pointing upwards, as it starts to take on directions that should be pointing upwards, it actually starts to be drawn pointing downwards until actually it's pointing directly to the left. Then it all lines up again. The ant should have turned, 180 degrees. Instead, it turned minus 180 degrees, but that happens to be the same thing. So now we got it. Okay, so we got that figured out, and this sort of maybe will convince you of something that I explained to the class this morning. So how many of you know of this guy named John Carmack? Yeah, just a handful of you. So John Carmack is like the original creator of really good 3D first-person games. So back in the day, there was Wolfenstein, Doom. More recently, you've probably seen Doom 3, Doom 4. The graphics engines that drove Doom 3 and Doom 4 are used in many other video games. They're licensed out. Nowadays, John Carmack is he's involved. In fact, I think he's part owner of this company called Oculus Rift. Have any of you ever heard of that? Yeah. So Oculus Rift, it's this incredible virtual reality headset that actually makes you feel as if, when you turn your head, the image that you're seeing turns exactly as it should. You can look at videos of people using this thing and in some cases becoming really scared by it. The guillotine example is a really good one. That's one where people can look up and see the guillotine getting ready to come down and chop their head off, and it's realistic enough to disturb them. So the guy's a real pioneer and has really pushed the limits and of graphics and games, and more graphics than the games themselves, for decades, going back to the early 90s at least. And if you ever read interviews with him, people always ask, what do you recommend for game programmers? And he recommends a few obvious things. Get lots of books on programming, do all the exercises. But the other big thing that he recommends is paying close attention in all your math classes. And in fact, even going back and looking at your high school mathematics again. Because ultimately, a lot of the problems that come up that can either be very frustrating or very easy depending on how well you know this basic mathematics. So simple things like trigonometry, linear algebra, maybe some basic calculus. Those things show up constantly in any kind of system in which you're simulating a physical system. So games are an example of that, but any kind of realistic simulation of any kind, whether it's a scientific simulation or whatever, you're constantly solving these little problems of trig and everything else. And you can either be really good at this stuff and solve those problems in a couple of minutes, or you can spend days trying to figure out what the heck's going wrong with your code. So it's worth investing time in getting really comfortable with the math. Okay, so we've got that working. So now there's a couple of ways we could go. In this morning's class, I worked a little bit harder on this turning aspect and set it up so that the turns were smoother. So the ant didn't just snap directions, but actually slowly turned. That's surprisingly hard. In fact, what's surprisingly hard is to get the ant to turn in the short direction. So if you want to make an ant that's like Derek Zoolander and can only turn left, that's fairly easy to do, but that means when they make turns, even if they only want to turn 1 degree to the right, they'll turn 359 degrees to the left instead, which doesn't look realistic. But you can get that to work, and if you want to see how that works, you can just look at the video from this morning's lecture. But another sort of realism problem with this game is the ant's legs. The ant's moving, but the legs aren't, and it just kind of looks like he's stuck on a magnet or something. So I'd like to see how to, maybe we can take a quick look at how to fix that. So what I did was I opened up this image with a photo editor, and I made 3 different versions of the ant in which his legs are bent in some of the versions. So there's an ant 0, an ant 1, and an ant 2. So we would like these things to, these legs to look creepy and wiggly. So when we load up the ant, maybe we'll also load up these images. Everybody see what I just did there? Okay. So create an array with 3 images. Those images will be called antgamesomething.png, or named antgamesomething.png, where that something is 0, 1, and 2. And what we're going to do is cycle through these 3 images that somehow look like this thing is walking. So we'll want an image index, and we'll start with the image index being 1. So it can be 0, 1, or 2. And when it's time to display the ant, we won't just use the stock image, but we'll use self.images at image index. Self.image index. Image index. There we go. Okay. So let's just make sure we still have something usable. So now it just looks like an ant with broken legs. And that's because we're not changing the image index. We're just always showing the same image over and over. When should we change this image index?
After you draw it.
After we draw it? Let's try that. So we want this image index to cycle 0, 1, 2, 0, 1, 2, 0, 1, 2. And so that means we add 1, and we do the whole thing mod 3. So let's see what that does. Now the ant's crawling. So maybe after we draw it wasn't quite the right time for this. Right, because we're always drawing 30 times per second, even if nothing is moving. So maybe it's only if the ant is moving that we should change this image index. And so that's in move. Good. So now the ant's sitting still, and it creepily crawls to its destination. So, so this is called, well, it has a bunch of names, but this is a poor man's animation, and all of these older video games that you've seen things like Super Mario and so on, where he's running, this is really what they're doing. They just have several different pictures of Mario in different states, and they cycle through them so his legs look like they're moving. But now we're getting, somewhere where we have something that's not super unrealistic, except for this snap turning business. Okay, so I think in the next 10 minutes we can even get the turning to work really nicely. So if we want this ant to turn a bit more realistically, then so we don't want it to just go get its food and do that and immediately change directions. We'd like it to actually have a direction that it's going in, and that direction changes slowly over the course of several frames. So maybe what we want, and instead of this vector UV that the ant is pointing in, there's another way to represent the same information, which is just saying what the ant's direction is. And we'll use an angle measured in radians. So the vector 1, 0, which is on the position 1 on the x-axis, that's really 0 radians. So instead of UV being 1, 0, we can just set its direction equal to 0. And now here, instead of saving UV, we can just say self.direction is equal to math.atan 2, UV at 1, UV at 0. So this is all the same. We're saving the same information, just in a different way. Instead of a point on a circle, we're just telling what the angle is that that point makes with the x-axis. And so who else uses UV? That's this guy. Now, if instead of having this vector UV, which has an x and a y coordinate, I have a direction, how do I get back to x and y coordinates? No, direction is just one number. It's just an angle. So how do I turn an angle into coordinates? Yeah. Yeah. So the x-coordinate is just the cos of that angle. So that's self-direction. And the y-coordinate is just the sine of that angle. And now we don't even need to do this calculation when we draw, because we already have the direction. So we can just say theta r is equal to self.direction. So let's see if we broke anything there. So it works exactly the same as before now. Sometimes when you're doing this kind of stuff, it's good to let it play for a little while, because occasionally there are bugs which creep up only when the thing is going, from a positive, the top right to the bottom left or so on. But this one I think we did properly. So nothing's changed now except for the way we're representing the direction of the ant. It's just represented as an angle. But what we would like to do now instead is take that calculation, don't snap the ant directly to that direction when we choose our food, but rather when we're moving, we do two things. We take a step forward in the current direction, and then we also turn a little towards our target. Okay, so now we're back to computing this vector when we're moving. And that's because now we're going to keep a direction, our own direction, which is not necessarily pointing directly towards the target, so we want to keep doing that. And there is the direction we want to travel in, which we get by saying, won't call that self.direction, we'll call that theta. Okay. So theta is where we want to go. And it comes from math.atan2, and therefore it's a direction between minus pi and pi. Now, I would like my direction to be also between minus pi and pi. So I'll put in a really ugly, hacky piece of code that takes care of that. It's not the best way to do it, but it'll really make sure that it works. So if our direction is less than minus math.pi, then we can say we can add 2 pi to our direction, right? So if I add 2 pi to a direction, I really get back the same direction. And if our direction is greater than math.pi, I can subtract 2 pi. Okay. So now what we have is the direction that we want to go to. It's called theta, and the direction we're going in, which is called self.direction. So let me write this in, hacky code. So exercise for you, figure out how to do that using modular arithmetic instead of while loop. Okay, so now we want to get ourselves turned in this direction. So what have we got if we draw this pictorially? We have these two directions which are between minus pi and pi. So we can draw them on a line like this. We have maybe the direction that we're currently traveling, and we have maybe the direction that we want to go in. And so what we would like to do is get a little bit closer to that direction. Well, if we didn't. So what we would like to do is basically immediately turn to that direction, but we want to slow that down a little bit. So if I take this thing and I say something like, let's do it, start the other way first. Theta and direction. So now, if this is what my picture looks like, this is the direction that I want to go, this is the direction I'm going. If I take a turn of theta minus direction, then theta minus direction is a positive number, right? Because theta is bigger than direction. It's this positive number that represents this difference here. So let's turn is equal to theta minus direction. Now, is this always the way we would like to turn? So do we always want to, let's say our direction theta is up here near pi, we're down here near minus pi. Do we want to always turn that way? So that's the equivalent of, let's say, a direction theta up here, our direction down here, So we're facing this way. We want to face this way. And if I start, moving along, taking direction closer and closer to theta, that means that I'm rotating this thing this way. Is that really how you would change directions? So if I want to turn 1 degree to the right, do I turn 359 degrees to the left? No. Only Derek Zoolander does that. So something we'll want to do is say, well, if the turn that we're asking to do is bigger than math.pi, then instead we should turn, it will be turn minus math dot 2 times math dot pi. And similarly, if we're trying to turn counterclockwise by 1 degree, we don't want to turn clockwise by 359 degrees. So if the turn we're asked to do is less than minus math dot pi, then instead we should turn, I think we want to do 2 times math dot pi plus turn. And now we don't want to turn the whole way. Instead, we want turn is equal to the minimum of divided by turn. And now we turn. Okay. So we figured out the way we would take the turn if we did it in one big step would be to do this whole turn, but I won't allow you to turn more than this amount or this amount. So I won't allow you to turn more than minus math.pi over 20 or math.pi over 20, and we better tie that to the speed. And we'll see if that works. No, forgotten self. There we go. Oh. Darn it. Tell you what I can do is copy it from this morning's class. That's okay because I wrote this morning's code as well, so it's not plagiarism. Yeah, we can look at the difference. Okay. Turn is theta minus self dot direction. If turn is less than minus math 2 pi, if it's bigger than math, turn minus 2 math pi, turn math dot. That's the same code. Aha, yeah. Okay. See if that works. No. The cert line just checks to see that there's some condition that's not completely bogus. Let's just copy some more code. Oh, what's that? I think we're, yeah, but that's just a comment. and I think it's code. You get 1, you get 0. No, there's a bug somewhere else. Anyway, I'll fix it, and you can check it out. Yep.
I had a question. You said plagiarism earlier when you said I can't copy the code, I got the code to this map. I was wondering if we'd used in our assignments little parts of your ant game code, is that plagiarism?
So you're free to use things that we do in class,
Okay.
but not things that you grab off the internet.
Yeah, no, I wanted to make sure.
If you do use something off the internet,
You have to cite it.
you have to cite it.
Yeah, no, I know that.
Yeah.
Where I didn't, because I wrote a lot of the code, and I would go back to your ant game program because it's very efficient.
Yeah.
And I'm just like, okay, well, this is exactly what I need.
Yeah. So that's, I mean, essentially, that's why I developed these games in class, so that there's a bunch of different little recipes in there that you can
Yeah,
use
like that's
inside your.
why would he give us this
your
if
own
we
stuff.
can't use it?
Yes.
On that note,
Yep.
unfortunately, while creating my webpage,
Yep.
I went back afterwards and went, because like reading all the syntax and stuff from the documentation, afterwards I went back and went, crap, this is as close as I've ever been to textbook code without actually copying it.
Yeah. Okay, that's fine.
Because I mean, everything that, like all the variable names and such are different except for URLs is still URLs because, well, it's the only thing that makes sense for that.
Yeah. Well, and I mean, you didn't get a particularly original assignment, right? I mean, it's basically do some of the exercises in the book.
Yeah, so what I did is I produced a web page that generates a business card template.
Okay, so that's good. Now, for this week, I'm not sure. What to give you, because essentially this week's assignment for the rest of the class is just about getting familiar and comfortable with Pygame and actually having a game with maybe a few different states and so on, doing some of these geometric calculations, and so I wonder if ultimately this week is sort of a warm-up for next week, which is they make their own game. So I don't know, for you probably what you should start thinking about is, well, you can make any kind of application you want, whether it's a game or whatever, but it should be, rich enough in that it has several things in it. User input, it should have more than one state, so for this state really means different web pages, different forms. In the book he does basically a text adventure game as a web thing. So basically this week I think you should try and figure out what it is you're planning on doing for a game and learning how to do whatever it is you need to do to get that done.
I've also been looking into various other Python packages for just making the browser application more interesting.
Yeah.
So I looked into media packages and such, things to embed video, all that kind of stuff.
Well, so if you think it's useful for your for the end goal of what it is that you plan on doing for a week and a half from now, then learn it and send me something or submit something that demonstrates that.
I think it could be useful, so
So basically,
I'll probably
then
do a few things. I'll probably give something that shows a bit more in-depth text use and something that shows media use. Or
yeah, okay. So that's fine, and then maybe include a note with it or something that says, explains why this is the package you decided to explore or use, and say, you know, next week I'm planning on making an application that does this, and I think video would be helpful. I think sound would be good for that, or I'm making an online game that that works some way, and I think, you know, what I did this week will be useful while making that.
Yep.
'Cause
I always
ba-
have a README file.
Yeah. So, because essentially for the, you know, that's the way things sort of work in this course, is we have to do some exercises to flex our muscles, and then we can actually build something that's interesting to us. And unfortunately, I don't have a bunch of exercises ready for web programming. So you're sort of going to have to figure out what it is you want to do there. But anything, I mean, do anything reasonable, and then for next week's assignment, we'll actually make some actual guidelines on maybe this kind of stuff that should be part of this this application or game.
Alright,
that
is
you're
next week most
developing.
definitely going to be a game, or is...
Definitely. I was going to post the assignment today, but I didn't have enough time. Because I want, this is in some sense going to be for many people, it's the pinnacle project of the course. After this, we go back to learning algorithms, which there'll be some coding and designing efficient algorithms, but they won't be big programs. They'll be back to, you know, write a function that does this and does it efficiently. Those kinds
out
of
of curiosity,
things.
I noticed that we're planning on doing Java at the end of this course.
Yeah, we have to.
How are we doing that, so I can try and figure out whether it works or doesn't work?
Command line. So text editor to edit Java programs, and compiler at the command line for compiling them. And
So the exact same way as we're doing with Python?
Yeah.
Oh,
So
the
we
next
don't
one.
need like Eclipse or anything.
Nope.
Alright.
That's why, because I know Eclipse doesn't work.
Yeah, you'll have plenty of opportunity to use IDEs later, already next semester. So yeah, I want you guys to actually do this stuff on the command line, because it will come and help you a lot later on, because IDEs only take you so far. Eventually, there's something you need to do that ultimately is something that's actually an easy thing to do on the command line, but actually in the IDE you have to hunt down through a bunch of menus and settings to find a place where you can enter, for example, some arguments that are passed to the command when it's executed.
Yeah, like
The
one
real
of our
pain.
earlier assignments, we just had to incorporate. Actually, that was for our 5th assignment. We had to incorporate a text file of some variety, and that'd be for lack of a better term, it'd be a pain in the ass.
Yes,
To do
yeah.
it through an IDE.
Yeah, no, so, you know, for example, I frequently get second-year students who you can ask sort of the simplest thing, the form, you know, write a program that opens up a text file that you've specified on the command line that's passed in as an argument, and prints it out, and they have no idea what that means. Command line, what's that? Even if they do know, they don't know how to test it, because in their IDE they don't know where to go and put command line arguments to pass to this thing. So if you know that early on, then, you know, when you get to using an IDE, if you ever do, you'll realize what, you know, somewhere these things that should be happening in the background, or maybe you just get fed up with the IDE and go back to the command line for that.
I'll
kind of
probably
stuff.
just stay with the command line.
Yeah, I mean, for you, I think text editor, I mean, the IDEs are not super helpful, right? And if you can't see what they're doing, like, they're great sometimes because you have this big API that you can't possibly remember all of it, and so they do some kind of auto-completion drop-down things, but it's not particularly useful if you can't see them. I mean, things, a little drop-down menu sort of pops up beside the cursor that you can select from to do a completion, but in your case that's not particularly helpful. So, yeah, So Java for the last 2 weeks, basically.
All right.
I'm just not sure what it's asking on the assignment for direction equals 0.9 times direction of this vector.
Yeah. So like the ant in this example, your thing will always have the thing that's chasing the cursor will always have some vector that it's currently traveling along. So, there's this vector that's, we'll call it direction, and it's at 0 or at 1. That's the x and y coordinates of this thing. So at each update, when you move, you're going to do something like self.position at 0 equals plus equals direction at 0, and then same thing at 1. Right? So that's basically the one step in the movement is you take your current position and you add this vector to it. That tells you what your new position is. But now the direction itself will also change. And the way it changes is you take both its components and multiply it by 0.9. So it kind of gets shorter. And then you add the unit vector to the new thing that the new position of the mouse. So for example, let's say here's the mouse cursor over here. This is your current direction. It's not pointing directly to it. So the first thing that happens is it gets shorter. So that just means you multiply both its components by 0.9. And then you'll add a unit vector pointing directly to the mouse cursor. And that just means that you add the component, right? This has two components, a 0 and a 1. This has two components, a 0 and a 1. You add those together. And then, so ultimately that will give you a vector that actually looks like this now. It points a little bit more towards the mouse than it did before.
Okay, so direction is supposed to be the direction that was the vector of the previous frame, basically.
Yeah.
Okay.
So it's the vector of the previous frame, and then
a little bit less than that.
Yeah. Well,
Okay.
yeah, a little bit shorter, but then added with a component added in, which is pointing directly to where it wants to go.
Okay.
And that's when you do that. This is sort of like almost a physical thing that you have inertia, which wants to keep you going in the same direction, and then some force, which is this thing, is pushing to actually get you pointing towards the cursor. So that's where you get this weird behavior of the ball, looping around this thing and finally zooming in on it.
It's very similar to the way that when you're dealing with gravity, you multiply your quadratic by negative 4.9, because you have to multiply by half gravity, which is the force of
So
9.8.
with all of these things, we're usually just faking some physical system, because real physical systems don't just update themselves 30 times a second. But, so that's where this behavior comes from. And you can see if you're not careful with this, for example, if you don't include this 0.9 multiplier, then you can get the thing that basically just shoots off the screen. So it's unable to stop itself to come back to and get to the cursor.
Okay. All right. Thanks.
Yep.